you should start thinking of a team, the Purple Common Math Competition. If you want to do it, it's a team math competition that we talked about last meeting, which is teams of 1 to 6. Registration starts in early February, so it's better if you just figure out your team earlier. You can also look at sign up for the CMC school visit, which can be pretty useful if you want to attend the University of Waterloo, or if you want to just learn more about the different math contests that are run throughout the year, as well as different careers in mathematics and computer science. And then finally, this isn't something that you can register for at our school, but if you want to do the AMC, which is the American Mathematics Competition, so it's either grade 10 or grade 12, you can register at an external institution such as Olympiad School. I think the final deadline to register should be in either late December or somewhere in January, because the competition is in February. So if you want to do the competition, you should register as soon as possible. So that's basically the end of the summary of the housekeeping items. So Bill is going to be giving his lesson on, I think, a competitive math topic. So yeah. And also, Miss N, can you record the lesson that Bill gives too?
Do you want me to start recording right now?
Sure.
Okay. Is that okay with all of you? Is that fine?
Yeah. Alright, can you see the screen? Okay. So I'll start. So my name's Bill, and today I will be talking about a concept in combinatorics, which is known as bijections. So bijections are a really powerful tool that can be used to solve hard combinatorics problems by converting the problem into a simpler problem, which can be easily counted. Okay, so before I talk about what bijections are, let's first review sets and functions. So a set is a collection of unique elements. The elements can be pretty much anything as long as there is some way to differentiate between them. In this way, a function is a relationship between two sets. It tells you how to go from elements of the first set to elements of the second set. We say that the function maps elements from the first set to the second set. And the only requirement of a function is that elements of the first set can map to at most one element of the second set. So here in this diagram we see there's a function from set x to y. In essence, a bijection is a special type of function between two sets in which each element in one set is paired with exactly one element in the second set, and each element of the other set is paired with exactly one element of the first set. So as we will see, the properties of bijections make them really useful in combinatorics problems. Okay, to see what a bijection looks like, here are two diagrams showing a bijection as well as a normal function between two sets. So see in the left diagram, there is a bijection between set x and y because all elements in x map to exactly one element in y. If we imagine that the arrows are reversed, we see that all elements in y map back to exactly one element in x. A bijection is also referred to as a one-to-one correspondence because each element in x has its unique corresponding element in y. And on the right, we see that this function is not a bijection because even though all elements in x map to exactly one element in y, see that c maps back to the elements 3 and 4, so this function is not a bijection. So in general, there exists a bijection between two sets if and only if they have the same number of elements. So this intuitive fact is actually quite useful. Okay, so how are bijections used? They are used to simplify complex counting problems. A usual type of combinatorics problem is to determine the number of elements in a particular set. That is to say, we need to determine all elements which satisfy certain criteria. However, counting the elements in this set is too difficult. It is sometimes possible to simplify the problem by establishing a bijection between elements of one set and elements of another set. by establishing a bijection with the original set and the second set, which is easier to count, we know that the number of elements of the second set equals the number of things we're trying to count, so we could find the answer that way. So now the only challenging part is proving that a bijection exists, and I'll show one general method to prove this. Okay, so in the first diagram, we're trying to determine the number of elements of the red set. So we don't know how many elements there are in here, so we will establish a bijection between the red set and a blue set, which has a known size, meaning we could easily determine the number of elements here. So if we prove that each element in the red set maps to exactly one element in the blue set, which are shown by the forward arrows, and every element in the blue set maps to an element in the red set, shown by the backward arrows, then we have shown that there's a bijection, and we can conclude that the two sets have the same size, so they have the same number of elements. Okay, here's a classic counting example that uses a bijection. So how many subsets are there of the set X, which contains the integers 1 to 8? So it is widely known that there are 2 to the n subsets of a set of size n, including the empty set and the complete set. So we can instantly say that there are 2 to the 8 subsets of X. However, we can analyze this problem further. The reason that there are 2 to the 8 subsets of X is that there's a bijection between the subsets of X and binary sequences of length 8. We can prove the bijection as follows. For every subset that you are trying to count, you can construct a binary sequence of length 8 by setting the ith character to 1 if the ith element is in the subset, and 0 if it isn't. In this diagram, we see that, let's say that we have a subset 2, 5, 6, 7, and then that would correspond to the code 01001110. So it is clear that applying this transformation on a subset will only yield one possible binary sequence of length 8. The reverse transformation is similar. Take any binary sequence of length 8 and add the number I to the subset if the ith character in the sequence is 1. So the operation of turning a sequence into a subset yields exactly one possible subset of the numbers 1 to 8. So we have proven that a bijection exists between the subsets of X and the binary sequences of length 8. So the two sets are actually the same size. There are 2 to the 8 such sequences, so there are 2 to the 8 subsets of X. Okay, now let's move on to another interesting example. Given a 4x4 grid, how many different paths are there from the bottom left square to the top right square if you can only move right and up? So, for example, here are some different paths that can reach the top right square. And our goal is to count every possible path without missing any path or counting a path more than once. Okay, we could try and draw out all of the paths, but this is extremely impractical because you may need to solve this problem for a larger grid. So we will simplify this problem by establishing a bijection between the set of all valid paths and some other set. In this case, you can notice that a path is completely determined by a sequence of two operations, which I will call move up and move right. To illustrate this transformation, take some valid path that we're trying to count. The transformation on a path is as follows. Just start from the beginning square and add the corresponding operation to the sequence, depending on whether you move right or up. So it's clear that applying this transformation to any valid path only creates one possible sequence. So in this case, this path corresponds to 2 moves right, 3 moves up, and 1 move right. Another observation needs to be made here. Every valid path that we are trying to count always involves a total of 3 moves right and 3 moves up, because we can only move in those two directions to reach the top right square. Thus, when the path is transformed into a sequence, that sequence will always contain 3 up arrows and 3 right arrows. The reverse transformation follows similarly. Take any sequence and construct a path from the bottom left square by applying the operations in the sequence. Yeah, this transformation yields exactly one path, and it is guaranteed to be valid because each sequence always has 3 up and right arrows, meaning that the path constructed always arrives at the top right square. So we have thus proven that a bijection exists between the set of valid paths and the sequence is made up of 3 up arrows and 3 right arrows. So now we need to determine the number of elements of the other set, and it is evidently much easier to calculate. So the number of ways to permute two groups of 3 identical objects is 6 factorial divided by 3 factorial squared, which is 20. And it is equal to the number of paths from the bottom left square to the top right square if you can only move right and up. So yeah, this concludes my presentation about bijections and how they can be used in combinatorics problems.
All right, thanks, Bill. That was great. So we'll go over some just housekeeping items that we have. I think Jason went over them briefly at the beginning of the meeting. Of course, the purple math competition is coming up in a